the dimension is bigger than 3. This is a widely accepted phase diagram. Let me explain, make some comments about phase diagram. So here Tc is the bulk critical temperature. So when it's for T above Tc, the system is disordered. So when the x-axis is K1 over K, so when the boundary coupling is small, it orders at the same temperature as the bulk. So this is this line is called the ordinary transition. But when the coupling is big, we are in this region, and the boundary can order at a higher temperature than the bulk. So as we lower temperature here, the boundary ordered first. So it's a purely boundary transition, because the bulk is disordered. The boundary order only penetrates in a very small distance. But if we lower the temperature further, we have this bulk transition. When the boundary is ordered, it's the so-called extraordinary transition, and the ON symmetry is broken because of the boundary order. And at the intersection point, we have it's a multi-critical point. It's called a special transition.
So what is SD?
SD means surface order, and BD means bulk order. O is D is a disorder, O is ordered.
And so this is a D larger than 3?
D is larger than 3.
Quantity? Or?
Quantity.
And this is for any n?
Yeah, when it's larger than 3, it's for any n. There are subtleties when D equals 3. I'll mention that later. So these transitions can be described by a quantum field theory at the critical points. So without a boundary, we know that the critical the OM model, the continued action of the OM model is described by this quartic interaction term. Here I is from 1 to n, and around 4 dimensions, this theory has a weakly coupled IR fixed point, which is known as the Wilson-Fisher fixed point, and at this fixed point, the critical coupling is of order epsilon. Now we put this Wilson-Fisher to study the boundary criticality. We put this Wilson-Fisher CFT in half space. So we just take y to be positive in this action, and it's known that, for example, the ordinary transition corresponds to perturbing the Dirichlet boundary condition of the free theory, and the special transition corresponds to perturbing the Neumann boundary condition, and the extraordinary transition corresponds to some OM breaking boundary condition. And there is an intuitive way to understand that this OM breaking boundary condition.
Sorry, but so that means that's a D less than 4, and a D larger than 4.
You can also have, for example, around the 6 dimensions, you can have there's a cubic description of the OM model.
Okay. And at very large D.
At the very large probably just mean field theory.
So it just.
Yeah. But I'll focus on D smaller than 4 in this talk. Yeah, that 60.
And strictly larger than 3.
Yeah. But I'll also mention D equals 3 later, because the most interesting case is D equals 3. I'll use epsilon expansion to probe D equals 3. Okay, to understand the boundary condition, let's put the theory in ADS. Why can do this? Because the ADS is the metric is conformally equivalent to a flat half space metric. So if it's a boundary CFT, it does not matter what background you use as long as it's conformally equivalent. And if we put the theory in ADS, we have this curvature term. And here I take the ADS radius to be 1. And now we have a non-trivial potential here. If I plot the potential, you have 2 saddle points. This is the kind of a trivial saddle points at phi equals 0. And at this set of points, if you expand it to run, if you expand around this set of points, you just have the free theory, just a conformally coupled scalar. So you can impose either Dirichlet or boundary or Neumann boundary conditions. But there can be other fixed points, and this is really this is actually a sphere of fixed points, and at this specific value. Here I choose the expectation value to align along the nth direction, and around this at this fixed set of points we have the extraordinary transition, and okay, in principle you can have two boundary conditions for a given mass, but at this point only one of them is unitary. That's the extraordinary transition. And okay, I'll make at another technical point that in ADS, the 1-point function is just a constant, because we know that if in flat space it's proportional to the distance to the transverse distance. Okay, let me just write. Is v2 delta is the dimension of O, and to define a operator in ADS, this is an operator in ADS. That's why it's a constant. This is the Weyl transformation. We will give an example of the 1-point function.
And Zimo Sun, on the previous slide, the two different ordinary and special, they correspond to the same saddle, but different boundary condition for the scale.
Yeah. Because in this case, both of them are unitary.
And they are related by the double trace.
Yeah, they're related by double trace deformation. And here I also summarize the RG flows among these fixed points. So at the special fixed points, we can turn the phi hat square operator is irrelevant. Okay. The definition of phi hat and the phi hat is that it's the leading operator in the boundary OPE of phi, so it's not necessarily equal to the boundary value of phi. For example, in around the 4 dimensions, we know we impose Dirichlet boundary condition at the ordinary transition. In that case, phi hat means dz phi. And similarly, phi hat square is defined in this way. Of course, the identity should not be included. So if we turn on a phi hat square deformation with a plus sign, we flows to the ordinary transition. And if there's a minus sign, it flows to the extraordinary transition, and it's a spontaneous symmetry breaking. And similarly, we can also we can turn on phi hat, and it also flows to the extraordinary transition. But it's a explicit symmetry breaking cycle. We turn on a magnetic field on the boundary.
Do you know why it's called extraordinary?
I don't know the history. Do you know why the name? And okay, there are some subtleties. The flow, actually, there's another name for the flow triggered by the phi hat operator. It's called the normal universality class, but it's believed that in D bigger than 3 dimensions, the normal and the extraordinary universality classes are equivalent, and also for icing in 3D. And the normal boundary condition extends to 2D. In 2D, it corresponds to fixing. For example, when n equals 1, it corresponds to fixing the boundary spin of icing. But the extraordinary class takes a modified form in 3D. This is work initiated by Max Matlisky, and there has been a lot of progress on this direction. But for this work, I will focus on the ordinary and the normal transitions. So everything continue from 4D to 2D. And we'll explain why I wanted to continue to 2D. Okay, there have been these boundary criticalities of the OM model has been tested extensively using numerical methods like Monte Carlo simulation or more recently conformal bootstrap. And last year, the fuzzy sphere regularization has been generalized to incorporate defects of boundaries in 3D IC model. And in particular, they can compute boundary essential charge, which I will review in the next slides, is, for the normal and ordinary boundary transitions of the IC model. And these numbers have not been computed in using Monte Carlo or bootstrap. And but the fuzzy sphere method has not been used for n larger than 1. Even without the boundary, OM model in general is a hard problem for the fuzzy sphere regularization. And the perturbative that can be compared with these numerical data has not been has been absent in literature, and we try to fill this gap in these papers. And we will also mention the perturbative calculation of other conformal data in this talk, but they are mostly focused on the boundary essential charge. So what's the boundary essential charge? Given a two-dimensional boundary CFT, the trace of the stress energy tensor is supported on the boundary, and here R hat is the ridge curvature and K hat is the extrinsic curvature on the boundary. So C is called the boundary essential charge. It decreases monotonically along the boundary RG flow. D1 is not monotonic. It's proportional to the homological norm, which is the two-point function coefficient of displacement operator. The displacement operator has a canonical definition, so its two-point coefficient is physical. And C can using this definition, C can also be extracted from the free energy on a hemisphere. Here R is the radius of the hemisphere, mu is some UV cutoff, and the coefficient of the log R term is basically the boundary essential charge. And as I mentioned, that we can also get this compute this number from using an ADS setup. And in the ADS case, the log R terms comes from the regularized volume. I'll also give an example later.
So what is that formula is a bit ambiguous. Is that C divided 3 log R, or is C over 3 times log R?
C over 3 times log R. Okay, but we cannot directly compute the free energy in 3D unless for large n, because the theory is strongly coupled.
So just to remember, the D1 you said that is related to a homological norm.
Yeah.
But there is no monoticity.
There's no monoticity.
There is no monoticity.
No.
So only positivity.
Yeah.
Yeah.
Only positivity.
Okay, so we want to compute something that's a function of D and extrapolates to F to the free energy in 3D. And around the 4 dimensions, we can compute it perturbatively. And a naive guess is this. Okay, here HD is means ADS, so it's hyperbolic, d-dimensional hyperbolic space. So it's free energy on ADS multiplied by some sign factor. Around this D equals 3, the sign factor captures the 1 over epsilon pole of the free energy, and the coefficient of this 1 over epsilon pole is basically the log R term. This is the reminiscent of the dimensional continuation of the A anomaly and in 4D and the F function in 3D. This F tilde here is proposed by Simoni and Eagle-Klempner. It's basically the sphere free energy multiplied by some sign factor. So here is just a very small modification compared to that, d to d minus 1, and the sphere partition function to ADS partition function. But it has a pole, but this F tilde defined here has a pole around the 4D because of the conformal anomaly. It's not a problem here because for the sphere case, because the sign factor vanishes around the even dimensions. So then the real quantity we will compute is this one, what we call S tilde. We subtract the ADS free energy by 1/2 of the sphere free energy. Then the conformal normally cancel out. And actually, this quantity is first proposed in this paper as a generalization of the C theorem on the boundary and defects. This quantity is finite around 4D, as I mentioned. There's no Y anomaly, and the sphere in 3D the sphere part does not contribute.
Maybe you look at the screen.
The sphere part does not contribute because of the sign factor vanishes. And the sphere part for the OM model is known around the 4 minus epsilon, around the 4 dimensions, and the epsilon expansion is known up to epsilon 2/4 to the particle order. And the say around at d equals 2, S tilde reproduce the logarithm of the boundary G function in 2D CFT. And to recall that the G given a boundary state alpha, the G function is defined in this way. So omega is the vacuum state, and you see the numerator can be identified as the partition function on hemisphere or ADS with the boundary condition specified by alpha, and here the omega is just a sphere partition function, and because the square root gives the 1/2 if we take a log. And for n equals 1, the G functions are known in 2D IC model. In many models, it's known due to Cardi. And for that reason, we will have 4 minus 1. We will have epsilon expansions around 4D, and we will have exact results in 2D, so we can do two-sided padding. And in 3D, the precise relation between S tilde and the C is given by this factor pi/6.
So away from the fixed point of the boundary RG, does S tilde make sense as a monotonic?
No, I guess it's not well if I have ambiguity. So it's like the
so it's unlike this boundary entropy that this same paper studied that is monotonic.
Right. I guess in 2D it's still monotonic, but in higher dimensions. Okay, then I'll just explain our main results. First, we discussed the normal transition. It's easy in some sense. So as we mentioned that at the normal transition, we have a non-trivial saddle point. So phi n has a non-zero valve. And then we expand the action around this valve. So A is from 1 to n minus 1, and the chi is the fluctuation of phi n. So the first term is the tree level, will contribute to the free energy at tree level, and the free action will contribute to the free energy at one loop order. And we will compute the free energy to order epsilon. And notice that the lambda is order epsilon at the Wilson-Fisher fixed point. So here the quartic coupling is order epsilon, and the cubic coupling is order square root epsilon. So to compute free energy at order epsilon, we need either 2 cubic vertices or 1 quartic vertex. And here are the diagrams. And this is a hard diagram. The last one is a hard diagram because each propagator is a very complicated hyperdimensional.
Before we get to the technical things,
no to mention technical.
the previous slide, I just want to make sure. So it seems to me that a more natural expression for S tilde will be in terms of the hemisphere boundary function with the boundary condition minus 1/2 of the boundary function.
That's the same as the ADS one because
right. That one may make sense along the entire RG.
Yeah.
And that may have monotonic property. Have people studied that?
No,
in those cases, I would expect the UV regulator dependent term to cancel between these two pieces.
Yeah. Here it also cancels.
No, but here, I mean, to make the relation between f on HT versus f on the hemisphere, you use conformal symmetry.
Yes, yes. You
Yes.
mean in that case, yes.
That's right, with
Without
direct-
watching, but we
Yeah, so that may, that one
significant-
may actually have well-defined
Yeah.
behavior away from the
Yeah,
artificial.
but I'm not seeing this one. Okay. I won't mention any calculations again, it's too long. And I here just give the result. That's the result for the S-tilde function at the normal transition. And this 1 over epsilon 4 is not due to any loop divergence, not due to any UV divergence. It's just because of the tree level action, because we have it's 1 over lambda, and the lambda is other epsilon. Okay, with these results we can do Padé. But let's focus on the n equals 1 case. This is the S-tilde function for n equals 1. And in d equals 2, S-tilde is known exactly as minus 1/2 times log 2, because the normal transition corresponds to this state and these Cardi states, and which fix the boundary spin. And these are the Ishibashi states, and basically because the definition I gave is omega, or here in this case just 0 plus, and it resolves the coefficient to 1 over square root 2, and that gives the G function. So we can do two-sided Padé to epsilon times S-tilde, because we want.
Sorry, just a question from the beginning. Your original model, the one that you wanted to study, was easing in d dimensions, or was it ON?
ON.
So why do you talk about easing in 2 dimensions? What's
That's
your-
just a special case for n equals 1. And for easing, we know the G function exactly in 2D, but for OM models, we don't.
So you're extrapolating in dimensions and in n? You know?
No, we will discuss other n separately.
Mm-hmm.
Here's just an example where, because one reason I discuss icing is that the fuzzy sphere people can do icing, and I want to compare with their results.
Well, I mean, Isaac is n equal to 1.
Yeah.
So
Yeah. But I'll also mention the higher n.
He has formula for general n.
Yeah, it's a formula for general n, right?
Mhm.
I just plug in n equals 1 and compare with the fuzzy sphere result.
Those polynomials in n, they have some zeros. I guess a pretty large n maybe, but
You can do it. It was for any arbitrary n here.
right. So I'm just asking the coefficients in this expansion. There are some zeros. If you go to probably large n, do they mean anything?
You mean these coefficients? Sorry.
The polynomials in the numerator.
Yeah.
That's just when, because this term is basically the one loop. Okay, the tree level cancels the one loop one. That's when, if we expand the tree level one to all the epsilon, to all the one, it cancels the loop one loop. But that's for some I don't know what's n. It's not
Yeah.
integer.
It looks pretty big. Yeah, probably not accurate.
It's not integer. Here it's numerical.
But neither is the dimension.
And if I do Padé, these 3 Padés are available. I just manually average them. We get central charge minus 1.43, and the fuzzy sphere is minus 1.446. So it's pretty close. It's less than 1%. And for higher,
Is there a way to estimate the uncertainty of this?
no, not kidding. Okay, Padé is not really not that rigorous. It's the one way to get some intuition.
Maybe you could mention that Padé is a way to kind of resum the epsilon expansion.
Yeah. Right. Okay. And
But we don't really know why that works.
yeah, it's not.
Or if, right?
It does not work always.
It's not. I'll mention it does not work later. It's not always. It's
Epsilon expansion is really black magic.
Yeah. Not real science, probably. Okay. And for higher
Well, that's
end,
not quite true. People understand how to
if we
resum
do, if
them.
we know the large orders, it's probably
Yeah,
hard to
yeah.
do. But here we just have very limited
Yeah.
data. But just try the per day. It seems more well here. And
If you do not do per day, how does it compare?
it's much worse.
Much worse in like becomes like -2, like yeah.
It's 11% or
It's, as you can see, right?
Yeah.
These two terms are basically -1 half,
Yeah, it's,
and there's
it's
another
like 100%.
-1.
Yeah.
really fake.
Yeah.
Oh, no. It's like 11% because there's a factor of like
Of
3
three.
some. Yeah.
Yeah.
This relation between SC and S.
For higher end, we don't know the G function in 2D, so we can just do one-sided per day, and here are the estimates. But we need the fuzzy sphere people to confirm that.
What about large N?
Yeah, I mentioned large N. And in this paper by Max and his collaborator, they compute the large N expansion of boundary central chart directly in 3D to order n to 0. As you can see, it's for small n it's really bad, right? For n equals 1, it's roughly minus 1/2, and it's very far away from this point, the fuzzy sphere data. Yeah, that's for n equals 2 and 3. Does this answer your question? Yeah, I just want to, because for n equals 1, I can compare with the numerical data.
So the sign of this C, does it have any meaning? So here it's always negative, but
The sign, yeah, that's just the monotonicity. Right?
that's a sign.
Yeah. It's not like the 2-point function of t. You don't have that.
Roughly speaking, it's because you're imposing theoretic condition. You're removing
Yeah.
block degree freedom. So relatively, there's a negative C.
So negative. But it can be both positive.
It could be
It
both.
was- yeah. So for Neumann boundary condition, if free theory is positive. And then, okay, let's move to the ordinary transition. In this case, the propagator is easier because the scalars are conformally coupled. Here, here this is ADS. I use the embedding space coordinates. So x squared equals -1 is ADS, and the given 2 points, this is the ADS invariant. But the diagrams are much more complicated. We want to compute the free energy up to epsilon cube in this case. People have not been able to compute these kind of diagrams. In particular, FNG is a full diagram. ADS. Okay, almost the whole paper is devoted to computing these two diagrams. Unfortunately, it's too technical. I'm not able to talk about this here. And also, in this case, we need to include the curvature, at this order, we need to include the curvature quantiterms. So we need to add the action to the action, these curvature quantiterms here, H, W, E are just the curvature invariants. And it was figured out by these people that at this order, this coefficient B will contribute to the free energy. And they know what exactly the fixed point B.
What
would
is
be.
H?
It's just, in our case, just R. It's proportional to R.
E is not Euler.
Yeah, oh yeah. But okay, for ADS or sphere, it's still, yes, it's constant. Okay, let's just first mention byproduct, the 1-point function of phi squared. Because these are the diagrams contributing to the 1-point function coefficient at order epsilon squared. It's very similar to the free energy diagrams. Basically, we just strip off these the circles here. But there's the subtlety that we don't integrate these free index, free vertex. So in that sense, it's a bit different from the free energy diagram. But as I mentioned, the one-point function is just a constant in AES. So I can compute the integrated one-point function, which just multiply by the one-point function by the volume of AES. So once you compute the integrated one-point function, you also integrate these vertices. So it's really subdiagrams of the free energy diagrams. So we don't need to do extra calculations to compute these one-point function. And here is the result. Let me explain the notations. So phi square r is the renormalized bulk phi square operator. It's basically the bare phi square operator divided by the correct multiplied by the wave function renormalization of phi square. And the effect of n is chosen such that this operator has a two-point function coefficient equals 1 without the boundary, without a boundary. So it means that n minus 1 phi square, n minus 1 phi square is exactly 1 over x to some power. So just a normalization. And this effect of 2 is the standard boundary CFT convention. So we computed the one-point coefficient of this operator. Remember that. Just remember there's an n plus 2 times S3, n plus 14. But on the other hand, people have been using analytical bootstrap to compute phi two-point function in the ordinary translation, and they can compute the two-point function to epsilon square. So in principle, we can use that to extract the one-point function of phi square, because basically because phi square is in the OPE of phi. And if we do that, this is the result. It's different from what we have. And what's the issue here? Did we made a mistake, and why? Okay, we believe the bootstrap is correct. Okay, the reason is that, and we can, unlike in flat space, although this phi square r is a finite operator, it's not a primary operator. That's very subtle. So one way to confirm that is that we compute the one-point function of this operator on sphere. So this is the diagram we need to compute on sphere. And we find that it's not vanishing. And it's known that for a primary scale operator on sphere, it should vanish at the critical point. So if this is not a primary operator, what's the correct primary operator?
It could be a primary, but it's not of definite dimension. It's mixed coming from the curvature.
Yeah, that's the reason. Okay, you know that. Because around 4 dimensions, phi square has dimension 2, and the rich scalar also has dimension 2. So they can mix in principle. And to define a primary operator, we have to take into account the mixing. And a quick way to fix this coefficient is that we require the one-point function of this operator to vanish on sphere. Since we already computed the one-point function of this one on sphere, we can get the coefficient kappa. And because it's curvature invariant, the definition of a primary operator on ADS should be similar. We just need to change the sphere curvature to ADS curvature. So the R difference is minus sign. And if we compute the one-point function of this operator, which we think is a primary operator, it reproduces the analytical bootstrap result. So this is a quite non-trivial check of the calculation of diagram D to F, and it also clarify the definition of a primary operator on curved manifold. So this curvature quantum is not the same as what I mentioned earlier, that you put in the action. those are required to have a finite free energy, a renormalized free energy. But it's a difference. It's a curvature constant term. You need to define a primary operator. It's not for the purpose of renormalization.
It's also can be also understood as a kind of anomaly associated with the Weyl transformation, going from the flat space to the sphere in curvature.
And probably to higher orders, it's possible that this kappa can be divergent. Okay. Now let's go back to free energy. Here are the results. So order epsilon cube. The first line is the one loop result, and these are what we computed from the higher order diagrams. And here I also give the expression because it looks too complicated. I give numerical coefficients for when n equals 1. But okay, given such a huge expression, you won't do Padeli immediately. You want to check if it's correct. And we do a large n check. How does it work? So this is the expression for S tilde, but we know S tilde is just f on hyperbolic space minus f on sphere, and the sphere result is known, and it's being checked. So we just need to check the ADS free energy, and we expand the ADS free energy in n. So this is we expand the epsilon expansion result in n for large n. The first line is the free energy of a conformally coupled scalar with a boundary dimension d minus 2. It's known, and I'll explain why later. And what are these terms? That's what we want to check. Can we recover these terms from an independent large n calculation? That's what we are going to do now. First, let's briefly review that the critical OM model in the large n limit is described by this action. This is a bulk theory without any boundary. And sigma is an auxiliary field introduced by the Hubble-Stratonovich transformation. Now we put this theory in ADS.
Sorry, there is no sigma squared term there?
You can drop it at the critical point. And this action is very useful to do large n expansion. And once you put in ADS, you have this extra curvature term. And if we assume ON invariance, we can integrate, which means that the classical value, the saddle point of phi is just 0. Then we can integrate out phi, because it's just a Gaussian integral for the phi fields. And then we get the free energy as a function of sigma. This is the free energy as the order n. So the saddle points are just when the derivative of f vanishes, and these saddle points have been computed by Kashidani and Jombi. So these are the two symmetry preserving saddle points. The first one has a boundary dimension. The first one has the sigma star equals d minus 2 times d minus 4 over 4. And given this mass, the only one boundary condition is unitary, which is delta hat equals d minus 2. And that's why I showed earlier that the first line is just the free energy of a scalar with boundary d minus 2. And this corresponds to the ordinary transition. And the other saddle point is delta hat equals d minus 3. That it corresponds to the special transition. And see that the delta hat becomes negative when d is smaller than 3. That's why it does not extend when for below 3.
What happens at d equal to 3 with the special case?
That's I think you still have the special points there. Just
but the delta hat is not equal to 0, right?
Yeah.
It's positive. It's coming from over n.
Yeah. But I guess you have the 0 modes in that case.
It's not exact 0 mode.
Yeah, it's
lifted by over n.
if you consider all n, it's not. Okay, there are also symmetry breaking saddle points in this case, and the bound. Okay, I will not discuss these saddle points in this case, so I just skip. And it corresponds to the normal transition. I'll focus on the ordinary case, and the calculation for the normal transition would be similar. So okay, at order 1 or n to 0, the contribution to the one loop free energy is the one loop free comes from the sigma fluctuation. And for that, we need to know the quadratic action of the sigma fluctuation denoted by the sigma. It can be attained by expanding the free energy F sigma around the corresponding saddle point. And this is the quadratic action. So basically, G phi is the propagator of phi in this case at this saddle point. So the kinetic term is given by G phi squared. Again, I'm using the embedding space coordinates for ADS. And we need to compute the one loop determinant of G phi squared as an operator acting on functions of ADS. And how to do that? Okay. Let's say that if we ask this problem on sphere, for example, on two sphere, it's easy, right? Let's consider this problem on two sphere. So we're given a SO3 invariant two-point function G, how to compute its functional determinant. We need its spectral information like the eigenvalues and the multiplicities. It's easy on sphere because we know that it can be expanded into Lagrange polynomials. Here I slightly changed the normalization of Lagrange polynomials such that we have this addition formula. And given this expansion, it's clear that rho L are the eigenvalues, and for each fixed L, the multiplicity is 2L plus 1, which is given by the representation theory. Then we can compute the functional determinant of free energy, which is 2L plus 1 times log rho L. So the whole point is to find the coefficient rho L, and the multiplicity is fixed by representation theory. We can do a similar thing on ADS. Here is a okay, to find the rho L, we can just integrate G against the Lagrange polynomials because of the orthogonality condition relation. Here is a table summarizing the comparison between sphere and ADS. On ADS, the spectrum is discrete, so we have rho L takes values in integers. But on ADS, the spectrum is continuous because the space is non-compact, so the spectral density becomes a function of nu. Nu is a real number in this case. And the counterpart of Lagrange polynomial on ADS is known as harmonic functions. That's been studied by these people. And this is an expression of the scalar harmonic functions. And here the convention is that gamma A plus A, okay, here, maybe just write down the convention. Means the product of these two gamma functions. Okay. And no, it's the coordinate dependence is just it's just a hypergeometric function. And okay, we can given these harmonic functions, we can expand two-point function into these harmonic functions, and this rho nu will be the spectral will be the eigenvalues. And the analog of degeneracy 2L plus 1 is known as the pressure measure, which is related to the principal series representation of SO1, D. And here is the expression. These are just some normalization factors, and usually people call this part the pressure measure, but it's just a name. Okay, so we can expand the G phi square in these harmonic functions and compute the rho, and it's given by this integral. So this is basically G phi square with a non-trivial measure. And then this part is the harmonic function. We can do this integral, basically do some transformation of high geometric functions and expand it in a series, and can compute the psi integral term by term and then sum it up. That's so in the end, the spectral density is just a couple of gamma functions. The normalization is not important. Yeah. Okay, with the spectral density, we can compute the free energy in this way. We know what this pressure measure is. It's also a bunch of gamma functions, and we know what this rho is. Unfortunately, we cannot evaluate this integral analytically. It's hard. And it's hard to get epsilon expansion from this integral because the integral domain is non-compact. So we need a small detour. We can just see this function, this fx. So this part is basically the pressure measure. I just strip off all the normalizations. And this is just this vector. But instead of 3D minus 7 over 4, I keep it general. It's a function of x. So it's closely related to the free energy. Then I take a derivative of f. Turns out that after you take a derivative, it becomes this becomes a digamma function, and you can do the new integral. It's much simpler. And then you can integrate back, do the x integral. You can recover the f sigma, the free energy of sigma field. It's a much simpler integral. The integral domain is compact, and after redefining x, it becomes the integral from 0 to 1. And now, given this expression, we can expand the integrand in epsilon and do the x integrals term by term. And we get this expression. It turns out it exactly matches the Lagrange expansion of our epsilon expansion result. So it's a quite non-trivial check of the epsilon expansion calculation, because this calculation is actually much easier than the epsilon expansion calculation. It's just one loop. And also let me mention d equals 3. In the 3D case, both the pressure measure and the spectral density are elementary functions, and it's very easy to do the new integral. Look, actually here, x means nu. And that's what we have. It's the volume of ADS3 divided by 96 pi. And in the last step, we plug in the regularized value of ADS3. And R is basically the IR regulator, so it's the radius of the circle of a sphere at infinity. And this coefficient 1 over 38, 1 over 48 agrees with a disk calculation. So these people, they compute the same free energy of sigma in 3D on a disk or on a hyperbolic on a half sphere, and they get the same coefficient. As I mentioned earlier, that in this case, in the ADS calculation, the log R comes from the ADS volume. Okay. Let's go back to the STL function. So now we are more confident that it's a correct result. The epsilon expression is correct. But okay, in the ordinary case, turns out the g function is 1, so S tilde in 2D should be 0. But we couldn't do two-sided per day in this case, because all of them have a pole between d equals 3 and d equals 4, or d equals 2 and d equals 4. Basically, the reason is that, you see, all the coefficients here are negative, so it's hard for them to resum to something vanish. Usually, epsilon expansion have alternating signs. But we just we can only do one-sided per day, and that's our estimate for the central charge. But on the other hand, it's almost twice of the fuzzy sphere result. So there are two possibilities. Either we need a more sophisticated resummation method, or the fuzzy sphere is wrong. I tried to argue that it's the second possibility. I'll give a different, completely different perturbative calculation that's in favor of our for-loop estimate. So that's a defect setup. So now again we can consider OM model in the full space-time, and we turn on a positive mass deformation on a 2D surface. So it means that we add this action, this term to the action, and if the bulk dimension is 3, it flows to an IR fixed point, defect fixed point, which just cuts this space-time into 2 halves, and each half realizes the auditory boundary fixed point in half space, and it's shown by these people using an large N argument, and I think this year Bedo and Ifan had a more general argument that for these kind of pinning defects, it always leads to factorization. But we will consider 4 minus epsilon dimension bulk, and we will check these factorization property numerically using epsilon expansion, and we also use this setup to get a different epsilon expansion for the boundary central charge. So the first step is to compute the renormalization of H. For that, we just need to compute the bulk one-point function. These are the diagrams. These are the highest order diagrams we consider. And we use the Manning-Barnes technique. Some of them are evaluated using this package. And we found the beta function. So lambda is the bulk coupling and H is the defect coupling. From H from the beta function we can get the dimension of the phi square operator at the IR fixed point of the defect. And here, this is the epsilon expansion we got, and then we can do Padé. So in last column is the Padé result divided by 2. And the first column is a Monte Carlo calculation of the scale dimension of phi hat in the boundary case. And we see that these two numbers are very close for each fixed n. It's a sign of factorization, which means that the phi hat square operator at the defect fixed point is actually just phi 1 times phi 2, where phi 1 belongs to one of the boundary ordinary class, and the phi 2 belongs to the other boundary, they decouple, and that's why it's twice of the boundary value. So it's a very nice check of the factorization property, which has not been done before. It's like you see the difference is within 1% or 2%. Okay, given that, we can so with the factorization property, we also computed the defect central charge. Here it's denoted by B. It's defined analogously, and it can be computed by wrapping the defect on a 2 sphere of radius r. Again, the log r term of the free energy gives the defect central charge. This B. And we computed the 2 order epsilon to force. These are the diagrams. So these vertices are on S2, and these are bulk vertices, which are in RD. And then we compute the defect central charge for arbitrary n. And in 2D, the defect becomes a mass term in the full space-time. For example, in n equals 1, the UV series is the Ising model with central charge 1/2, and the IR and the mass term just gaps this series. So the IR series has a central charge of 0, and the B is just the change of boundary, just the change of central charge from UV to IR. That's so B should be equal to minus 1/2 for n equals 1. And we can do two-sided per day, and based on the factorization, we know that the boundary central charge should be half of the defect central charge, and we get this number, which is almost twice of the Fidesz sphere. So we did two independent calculations, and both of them are almost twice of the Fidesz sphere result. So maybe the calculation is wrong, or we need a different resummation method for the ordinary case.
Has there been attempt to calculate this number also from like Monte Carlo?
No. But it's really the only way we compute it. Okay. Some outlook. So, yeah, one way is to understand the puzzle of per day. We probably need to compute more high-order terms. And we didn't do the special boundary condition because technically we need to include some IR regulator. And we also here we developed the large N calculation for any D, but only to order 1. It's interesting to extend to order 1/n. So then, because we know that the larger expansion of the central charge is very bad without the 1/n correction. And these are high loop techniques in ADS can be applied to holographic setups. For example, the BPS Wilson line in n equals 4 can computed on this is localization result, but you can also compute it on ADS2 using field theory calculations, and this coefficient should be recovered by a two-loop calculation on ADS2. And so similarly, we can see the BPS Wilson line in ABGM, and this is just tree level 1. This is the one loop. We should be able to recover this term by using two loop calculations. Of course, in this case, there are infinite number of field contents. We also need to sum up all these contents, like in the high-speed theory.
From the KK modes?
Yeah, because it's ADS2 times S1, from the KK modes on S1. But in principle, it's doable. It's like two loop diagram already computed for loop diagrams. Yeah, thank you.
Recently, the Cesar and Richkov had doubts about the epsilon expansion itself for ON and the nonlinear sigma model. I mean, they had the computed nonlinear sigma model in an epsilon expansion, 2 plus epsilon, ON in 4 minus epsilon, and at epsilon equal to 1, they found a disagreement. So
they have this very special operator
that exists in one theory and in the other. So wouldn't that cast some doubts about this expansion, just even for the bulk, and a fortiori for the binary operator?
But that's not the same theory, right? It's the non-linear sigma.
Well, the point is exactly that you start with the linear sigma model and then you do an expansion. And you extrapolate from the 2, where it's well defined as So the question, if you want, is what we take ON in 4 minus epsilon, then you continue to epsilon equal to 1. Is that the model you started with? The ON defined as a stick?
With the lambda 4 action, quartic action, I don't think you have the same problem, right? If you start with the quartic interaction.
Why not?
Not the non-linear sigma. Do you have this?
Well, I mean, you start with the quartic, right? Otherwise,
Yeah.
the expansion would make sense. So,
Are you worried about the equivalence of?
of being inequivalent, yeah.
Yeah.
Taking
Yeah.
So going from the sigma model and then doing 2 plus epsilon versus the 5 to the 4th, doing
Yeah,
formalization.
exactly, yeah.
I think Zimo there he's doing exclusively just the format epsilon.
Yeah.
He's never matching with
I
the
didn't do the
2 plus epsilon from sigma model. So it's self-consistent.
Yeah. That's
It's inconsistent, but is it the model that we had in the first slide? Where we
Ah.
had,
Yeah,
okay.
like the one defined by
Yeah.
the Hamiltonian. Yeah. I think
that's
yeah.
But
It's
the-
believed
but
to
the
be
fun-
equivalent in 3 dimension,
yeah.
but
Because
but it's also the ON in 2 plus epsilon.
I agree.
is
Yeah.
believed to be equivalent. right?
yeah, but for the boundary center charge, we only care about for example 3D, and we only use the minus epsilon expansion for that.
But I mean, Massimo is asking like a more basic question, like in the beginning slide where you motivated this model is from this Hamiltonian
Yeah.
defined on this spherical, spin, right?
But
Whether
if-
that is actually described by the 5 to the 4th theory.
But yeah, but there
Yeah, epsilon expansion all the way.
consider from 3 to 4 dimensions.
Yeah.
We didn't really compute consider lower dimensions. Yeah, only for per day we sort of using the 2D data. But
I guess the
we
honest
don't
answer
have
is just we don't know.
Yeah, we don't.
I have a quick question. Can you say again the center chart for normal? What did you find? For icing normal in 3 dimensions.
It's almost the same value as the body sphere results.
But it should be smaller than the ordinary case.
Yeah.
So I wonder if there's a consistency check.
It's
It should be very just from monotonicity of RG.
yeah, that's true. It should be.
Forgot what
But
number.
in
it
that
was.
case, what we get something is probably bigger than the.
Should be more negative somehow.
Should be more negative. Oh, it's more. It is now. It is more negative.
I see. So it's like a much more
It's
negative.
more
-1.
because
Okay, good.
It's,
Okay.
it's minus.
So it
one.
doesn't-
That
doesn't
is
impose
0
any-
point. It
doesn't impose any
doesn't
check,
violate
yeah.
that,
Yeah.
That one is minus 0 point something.
That's right. That's right. Okay. So have you talked to any of the fuzzy sphere experts and see
No,
what?
because one reason that we want to check the calculation, so we only recently did the larger end
Mhm.
calculation.
I see.
Yeah.
So now you're confident.
Yeah,
with
we are
your-
not
okay.
confident with epsilon expansion.
Mhm.
Yeah. The larger end is not in the papers.
I see.
Any other questions? It's time to get a speaker again.
Yeah, thanks. Ordinary versus ordinary constant determinant of the